Thank you, Cherry. Good morning, everybody. Yes, my name is Chenoa Tremblay. I'm a postdoctoral researcher with the SETI Institute, and I'm hoping to talk to you and hope you enjoy the journey of why I have such a passion for looking for life at these meter wavelengths, these massive wavelengths of light. So our adventure to go find life in the universe has taken us on amazing journeys. It has taken everywhere from trying to understand life in all aspects of Earth itself, in all sorts of different environments, to the most extreme regions of the universe itself. Now, this has taken us to learn things like that if molecules that are the seeds of life were actually on an asteroid and collided with Earth, we now know that those molecules would stay intact. We can also learn that elements like phosphorus, which is thought to be indicative of life, can ride on an asteroid, and we can trace that all the way back to the stars. So to look for life, we really need to look everywhere. And for my journey, I have decided to go and look at these larger wavelengths of light itself. Now, the idea of low-frequency radio telescopes is not new. Some of the first radio telescopes in these meter or less than 1 gigahertz, if you like, frequencies, were built in around the 1970s. But in about 2013, there was a resurgence for the search for building low-frequency telescopes. And there's a couple of reasons for that. One is we realized that we could build simple dipoles, put them in desert at low cost, and make large arrays with small amounts of infrastructure and small amounts of teams. The other thing is, without upgrading the technology on low-frequency telescopes, we were missing pieces of the cosmic puzzle. So if we only focus at higher frequencies, we will actually be missing some of the story that we're trying to understand and tell. So in particular, over the last 8 years, I've been working on the Murchison Widefield array. Now, this is a telescope that is a precursor to the future SK low, or square kilometer array, low frequency array. And it's located in Western Australia. Now, this telescope observes between 70 and 300 megahertz, or if you prefer wavelengths, 1 to 3 meters approximately in wavelength. Now, we observe about 30 megahertz of simultaneous bandwidth, if that's of interest to you. And we can go and use this telescope for a number of things. Now, originally, these two telescopes, the future SK low and the MWA, had two major science goals. One is to understand the history of neutral hydrogen and the birth of the very first stars. The other one is looking at high time resolution and looking at pulsars and pulsar arrays, similar to some of the talks that were given yesterday. But the flexibility of the design of these telescopes had allowed me to take it in a completely different direction. And that's what I've been working on. So one of the main benefits of working with something like the Murchison Widefield array is the field of view. So like Cherry had said, I've been working on the Very Large Array, which is in New Mexico, which gives an amazing amount of detail, but covers a surface area of about 1/12 of the size of the moon for its field of view. Now, if we make that into comparison for the Murchison Widefield array, I can fit 1,600 moons in the entire field of view of what I can process. But the telescope is actually capable of viewing the sky of about twice that area. So we're a little bit limited by computing power. Whereas some newer technologies, like the phased array feeds that are on the Australian SK Pathfinder, is trying to meld these two worlds, where we can get large field of view and an amazing amount of detail. And I won't go too much into this, but it does exist. So typically, the search for life, as Steve had alluded to, has taken us to a journey to look for two different aspects. One is technosignatures, the idea that a civilization is communicating either amongst itself or with another civilization, or similar to what we do with our probes that are within the solar system, communicating with ourselves essentially, but with another device. or the search for biosignatures, which is the idea that not only the potential for an advanced life, but also something like the seeds for life or primordial life. And we consider these two things completely inclusive. So if there are amoebas on a different world playing Nintendos, we might be able to see them with one of either of these two approaches. Likewise, if there are robots that have been left behind by a civilization and continue to operate amongst themselves, we could also potentially find them. But for the context of this talk, we're going to keep this as looking for advanced life or looking for simple life. So why would we look for advanced life within low radio frequencies? Well, one reason is because that is one of the primary frequency ranges in which we are daily communicating. So whether it's digital TV, cell phones, satellites, or two-way radios, we're constantly using these frequency range below 1 gigahertz. So if we use it, maybe somebody else does. The other advantage is that with very large wavelengths, the waves are bigger than the dust particles without space. So therefore, they're going to travel further distances. There are a couple other reasons, which I'll go through through the talk. Why do we look for simple life at lower radio frequencies? Has to do with what we're learning as we build a database of molecules we found in space. So far, we've discovered a little over 200 molecules in space. And if we plot the atomic mass, or the total mass of the molecule itself, in comparison to the wavelength in which we can detect it, you can see that heavier molecules exist at lower frequencies. So if we extrapolate this down to meter wavelengths, we should be able to find larger chain molecules, like maybe proteins, or larger atoms, like phosphorus, at these lower frequencies. So it opens up another range in which we can search for life. So over the last 8 years or so, I've been working with a series of supercomputers and cloud environments to develop ways of using these low-frequency aperture array wide-field telescopes to look for life, both technosignatures and biosignatures. And it's been a wild journey. It has taken us through learning brand new supercomputers, working with the facilities, trying to get them to work, doing all of these corrections, and creating over 1 million images of the sky. Stacking some of these together and trying to see if we can find the signals that we're looking for. So the signals that I have been searching for in particular have been non-time varying narrow band signals. Now, narrow here is defined by a 10 kilohertz channel width, which is not the same definition of narrow that others might have. But what I do is I go back and periodically look at the same patch of sky and see if any signals that I have found are persistent. So in this case, this point source on the left is repeated in data sets that we took in 2014 and 2016 and matches up with the rest frequency of the molecule nitric oxide. So even though it's of low significance and fairly narrow, we are fairly certain of the result. But there's lots of stuff that we can find in this frequency range that can indicate something about what we are learning about the telescopes and for life. So one of the signals is neutral hydrogen. Hydrogen is prevalent throughout the entire universe. And as the wave of light for neutral hydrogen is moving through the galaxy and through the universe, it stretches. So that means even though it naturally emits at 1.4 gigahertz, its stretch means that we can look at galaxies that are where the light has been traveling for billions of years, now at these lower frequencies. So they're down to these 2 meter wavelengths. The other thing is recombination lines. We know that there are atoms out there that are ionized, and they pick up these free electrons, and then those emit light. Or molecules, like what I have been looking for, where they're rotating in space and they get energy from sun and various other aspects, and they change that speed. And when they change that speed, they also emit light. We also find ourselves a lot in the data. Radio frequency interference is not hard to find. It sometimes can be hard to mitigate. But we can learn about our telescopes, and we constantly do, by actually relying on that noise. And so we can actually use the strong signals from satellites to tell us something about our beam pattern, for example, on the sky. So we do find that, and sometimes it's useful, and sometimes it's just really annoying. But there's other things that we like to find in this data as well. So the search for dark matter, we talked about axions yesterday. In the presence of really strong magnetic fields, this might produce a spectral line type signature equivalent to the mass of that particle. So we might go looking for that. Or we might go looking for these technosignatures or signs of we can't explain away this signal, so therefore maybe it's another civilization trying to communicate. But constantly, as we go through this process, we also find unknowns. We find things we don't understand, we don't know about, and those can also be really exciting. So what I have done over this time is done 4 surveys. Each one of these cover, like I said, this significant portion of the sky. We've used the phase 1, or the first phase of the Murchison Widefield array, to do 2 surveys around 100 to 130 megahertz, one looking at the galactic center and one looking at the galactic anticenter, or Orion. And these covered 400 square degrees, which is that 1,600 moons, approximately. Then we used the phase 2 array to look towards the Vela supernova remnant, and you can see prominently this flower-like structure, which is called the IRAS supershell from the ancient supernova. Or we looked at the center of our galaxy again at a higher frequency. And overall, we can look at what is known, where the location of known exoplanets are, what are the signals. We can also compare with catalogs around the chemistry, or we can look for some various other unknowns. But like I said, the advantage of this wide field of view is not just to look towards places where we know to expect a signal, but all of the spaces in between. What if another civilization has sent out a probe somewhere? If you're only looking towards the precise location of where those exoplanets are, you wouldn't see it. So we have all of this space in between as well. So in one of these fields of view, if we compare it to the Gaia catalog of low-mass stars, then we get over 10 million stars in our one field of view. So now we can start playing around with some statistics and look for other places in which a signal might be derived and set some limits on that as well. But like I said, we can also look for biosignatures. We have, in these surveys, also found the potential for nitric oxide, SH, which is the mercaptan radical, formaldehyde, and a funky asymmetric oxygen molecule. So why is this interesting from a biosignature perspective? Well, nitric oxide is important to us because it is super important to our daily lives, the way our bodies work. If you go and you Google nitric oxide, you end up with a whole lot of supplements, specifically usually marketed towards bodybuilders, but really it's also really important for fetal development, and there are a number of research papers that suggest that it was also an important molecule for primordial soup. So if we want to find the early stages of life, nitric oxide might be one of those things to go looking for. Now, we can detect it at higher frequencies, but we're not detecting it as frequently and as often as we would have expected based off from natural abundances of the universe. So going down at lower frequencies might help fill in the gap. Also, the other 2 molecules, the formaldehyde and oxygen, have been used in laboratory experiments to prove that in space that is required for the creation of amino acids. So even if we don't have the sensitivity yet to detect something like amino acids, we might be detecting some of the pieces and bits that make up to those. And amino acids are important because they're precursors to proteins themselves, which we think are also critically important for anything that might be considered life. The mercaptor radical, although not particularly interesting from a biomolecular perspective, it is something that we use in our regular lives to combat some of the human-made emissions. So perhaps that could be important later on as well. Okay, so where are we going with this in the future? So currently, the MWA is upgrading itself to a new correlator and some new receivers. Currently, we have 256 of these dipole tiles spread out over 5.5 kilometers of the desert, but we can only turn on 128 of them at a time. So the upgrade to our receivers will allow us to turn on all 256 at once. Also, we have a new correlator, which will allow us to tune the frequency resolution, and so we can get much better resolution in the future analysis. Due to this upgrade, we're also able to build a brand new commensal FRB and SETITY monitor on the back end of the MWA, and that's work that has been initiated mostly through Danny Price, but through a number of other engineers and researchers at the telescope as well. I've recently had a proposal accepted to start a low-frequency SETI program on the Australian SK Pathfinder at 724 megahertz, and this is to look for both molecules and technosignatures in seemingly random parts of the sky that we don't tend to point telescopes at to see what we can find, but we do have some exoplanet data on. I'm also working with a multidisciplinary team at the University of New South Wales and La Trobe University in Australia to learn more about chiromolecules and its potential for emission at lower frequencies. This goes back to the idea that we can shift these main transitions at lower frequencies and potentially detect them because they're much bigger and they contain much heavier atoms. So this is work that we're very much excited for. Okay, we're also very excited for this future SK low telescope. This is, I can go back one slide. Okay, okay. These are these Christmas tree style dipoles. They're about my height, maybe slightly taller, that have two different structures, and these are designed to observe between 50 and 500 megahertz, and they'll be put out through the desert in this spiral style pattern. Now here, this again, some of the same main science drivers as with the MWA originally, but one of the main benefits of this is going to be its sensitivity. And so a projection of the sensitivity at both the low and what the SK mid is going to be in comparison to current online telescopes is going to give us an amazing boost to detect these things in the future. And so I'm really hoping that I've convinced you that low frequencies is a good place to go searching for life and that there's a lot of potential there and a lot of things that we can continue to learn. Thank you very much.